Good morning. So time is up. We got to go back to the session. My name is Yoichiro Tanaka from Toshiba. I will take this session as a chairman. And welcome to this session. And before we start the session of the device part 1, could you identify yourself, the second presenter and the third presenter of the session? Please identify yourself to us. Just a second? Okay, so. All right, so I'd like to introduce the first speaker, Shruti Patil from University of Minnesota. She will present Spintronics-based logic circuit using magnetic tunnel junctions. Let me introduce Shruti. Thank you.
So, thank you. I do want to thank you for this wonderful opportunity to talk about my research, and I never expected to have such a wide and a reputed audience that I would someday talk to. So I'm very excited to be here. I'm going to talk about Spintronics-based logic circuits using the specific devices of magnetic tunnel junctions. And though our research is actually focused more on Spintronics logic circuits, because this is a memory workshop, I'm going to make it relevant by focusing more about the fact that this particular work was done with magnetic tunnel junctions. So what really spin brings to the table is this new degree of freedom, this additional degree of freedom and additional capability. So even though we cannot really control and observe individual spins of electrons, what we can do is control a group of electrons, the spins of a group of electrons together, and observe the effects of this group of electrons. So that brings us to these interesting device structures called as the magnetic tunnel junctions, which, as we heard yesterday, and most of you would be familiar with, have these two different resistance states. The logic 0, which is a low resistance, and a logic 1, where the free layer and the fixed layer are magnetized in certain directions relative to each other. So the initial ways in which people used to control the spins of the free layer was this intuitive way, where you would use the effect that electric current produces a magnetic field around it. So that was also called as a field-induced magnetization switching. And there was this current plane on top of the free layer, and that would create a magnetic field which would change the direction of the free layer and so on. Now, the engineers were not really very happy with it because it ran into problems of scalability. But then the spin torque transfer effect was discovered, and the engineers now were very happy because it could scale very well. But happy is an understatement. It actually created a wave of excitement in the field of spintronics, in the field of MRAMs, and a lot of new research developments have happened since then. So let me revise the spin torque transfer effect for you. When a current is passed through the device from the free layer to the fixed layer, and if the value of the current is greater than a certain threshold voltage, then it changes the direction of most of the electrons in the free layer to be parallel with the fixed layer. And when a current is passed in the opposite direction, then the free layer aligns itself in a direction anti-parallel to that of the fixed layer. So from this, the magnetic tunnel junctions have walked this path where they have gone towards memory devices, where a lot of you may be familiar with the development, the progress, the issues, the challenges, and we will also hear about these developments in the later talks. But what I'm going to talk to you about is how do we use this principle, or how do we use these devices for accomplishing logic operations. So how do we really get a logic gate out of this? Oops, sorry. So this was proposed by Professor Wong and his students at the University of Minnesota a few years back. And what it really does is the current that is passing through the MTJ is coming from two different current sources. If these are the possible values of the current sources, minus I and plus I, then the net current that passes through this device is given by the Kirchhoff's current law. So in the first case, it's minus 2I. In the last case, it's plus 2I. So minus 2I means that the direction of the current in this device is from bottom to the top. And here it's from top to bottom. So here's a little cheat sheet for you. When current flows from bottom to top in this magnetic tunnel junction, then it writes a logic 1 to the device. So the state of the MTJ is high. And from top to bottom, it writes a logic 0. So the state of the MTJ is logic 0. And here I'm just assuming that 2I is the value which is greater than the critical threshold current of this particular MTJ. Now what happens in these cases? The net current through the devices is 0. So if we had started with an MTJ that was preset high, then at the end of the operation, what we have is this particular truth table, which corresponds to the NAND truth table. So if we had started off with the MTJ, which was preset low, then this would have been the NOR truth table. So great, we have the NAND and the NOR, but and in electronics, if you have the NAND gate, you can build almost anything. Unfortunately, that's not very true in spintronics. The resistance state of this particular MTJ does not exactly propagate to the input as a current input of another logic device. So what people do is they use sense amplifiers, just like in MRAMs. They use sense amplifiers to sense the data in the magnetic tunnel junction that converts it into an electrical signal, and then that is processed through processing circuits. And we'll talk about sense amplifiers a little bit, but before that I wanted to show you one of these interesting papers that was published in 2008. I think it was Professor Ono's group in Japan. And what they did was they used this particular circuitry and demonstrated the function of a full adder. So the inputs A and C are coming from electronic, so they are electronic inputs, and B is a spintronic input, that's a stored input. So they showed that this can do the sum and the carry function. And there are two very interesting things about this. One is that electronics and, one is that MTJs are being used as these devices for computation. And two is that electronics and spintronics are working together in some fashion to provide a logic function which could potentially have better performance than just an electronic adder. So basically they showed that this could potentially have a lower power than a simple adder and so on. So this was interesting for that reason. It also showed that you could integrate the two technologies and they could really work hand in hand. So coming back to the sense amplifiers, the problem that we were working on for quite a little while was this. We have these devices that can store data. We have this device which can perform a logic operation. What does it really take to go from here to here? Now it takes a lot of intermediate circuitry. What is that intermediate circuitry doing? It's reading this data, converting it into the kind of input that this logic device needs, and then it's applying it to that input, and that's how we get our output. So if I develop the details in this intermediate circuitry, then this is what we get from what we have seen so far. So there is a reference magnetic tunnel junction. The sense amplifier compares the resistance of the data MTJ with the reference MTJ, gives a certain output. Perhaps there's a right circuit necessary, or maybe not, depends on the parameters of these devices, depends upon the design of the sense amplifier, and finally that is applied to this particular logic gate. So there are a lot of overheads. It is very complicated. And another subtle thing is that the resistance is not just read out as not just converted into current, it's converted into a bidirectional current. So a sense amplifier has to be designed in that particular manner. The more important and more serious implication that this is showing is that every logic operation it comes with its own sense amplifier circuitry. Even though these data devices and this logic device looks exactly the same, the logic capability comes with a lot of strings attached to it. So it is a feasible operation. Maybe it will be lower power or faster than a corresponding electronic operation where these are non-volatile memories, and then this is a NAND gate inside the Intel Core processor, maybe. And data has to go through all these cache hierarchies and this entire pipeline and then be processed into its NAND output and then written back. Maybe it's better than that, but still it's not a very attractive picture. So we were trying to work on this, and we think that is one of the biggest challenges to trying to incorporate logic capability into these devices. So it turns out that there can be a really elegant way to get around this problem. So this is the circuit that we proposed. The resistance in this particular circuit is here. So if the first term is the parallel resistance of the input MTJs, and the second term is the preset low resistance of this output MTJ. So A and B are input, C is the output. When we apply a voltage at this terminal and ground this particular terminal, then there's a current that flows through this circuit. So let's suppose the currents that are flowing is I1, I2, and I3. What we know is that the relationship I1 greater than I2 greater than I3 exists in this particular circuit because of the values of these resistances. So if we can engineer this particular value of the applied voltage so that so that I1 is greater than IC greater than I2, then what we are able to do is cut off the truth table at this particular point, and since I1 is greater than IC only for the first particular case, the current that flows from bottom to top writes a logic 1 to this particular MTJ. So here's your cheat sheet back. When current flows from bottom to top, you get a logic high over here. For the NAND operation, you perform the cutoff at this stage, and so you establish the relationship I2 greater than IC greater than I3, and so only for all the three cases, the current that's flowing through the circuit is greater than the threshold current that writes to this MTJ. So you get a logic 1 here, and the MTJ retains its logic 0 state for the last case. So that becomes a NOR and the NAND operation. For the AND and OR, what we want is that current should flow from the free layer to the fixed layer. So current has to flow from top to bottom. So that's the change that's necessary for AND and OR, the exact same principle. And if you're still awake and still interested, you will notice that the AND and OR can be done by this exact same circuit by simply interchanging the values of the voltages on these two terminals. So if this becomes voltage and if this is grounded, current will flow from top to bottom over here. So this is some simulation where only in the first case in the NOR operation for inputs 0, 0, the MTJC, it changes its resistance after some time, and in all the other cases it doesn't. So obviously it works great in theory. What happens in practical devices? So we discussed this idea with our device physics team, and that is a brilliant team led by Professor Wong at the University of Minnesota. And they liked the idea, so they fabricated this proof of concept circuit. So this circuit looks like this on the wafer. That's the optical image. So basically, it's just 3 pillars of MTJs on a common bottom lead, and then the input, the 2 terminals are separated, and that's where voltages are applied. That's the nice curve that they got from the devices. And that verified that basically we are able to do the 2 input logic operations of NAND and NOR. They also did something very interesting with this. What they also fabricated were 3 input MTJs. Now, again, that looked exactly like it looked like the 2 input MTJs. There were now 4 pillars of MTJ stacks on this one shared bottom electrode, and then that was the graph that they got out of it. But what this allowed them to do, in addition with the NAND, NOR, and OR and NOT operations, was the majority logic gate operation. And the majority logic gate operation is also a universal operation, along with, just like NAND is, NOR is, and the set AND or NOT is. And also, the majority logic gate is a very natural function where spins are concerned. So if you've worked with any logic with spins, then MTJs, MQCAs, and these new interesting devices, all spin logic devices that are being proposed, all of them have this very natural capability. So it is of some interest in the spintronics community. So they were able to verify that particular function with this fabrication. So I can talk about some more work that we did. I can talk about the pros, cons, the immediate next step, the challenges, and so on. But I think I'll discuss a little bit about what this can mean for computing. Just want to open up that discussion, open up some ideas. So this particular structure here is this very classic 1 MTJ, 1 switch circuit in the memory. So this is the single MTJ, single switch, or single transistor circuit replicated 3 times. And that has a very nice regular structure to it, a very nice memory array-like structure to it. The logic structure that we just saw was this particular structure, and even that has a very nice regular feel to it. So if we combine these 2 circuits by brute force, then what we get is something that looks like this. And this, if it extends in both directions, it still looks quite regular. So what can, and I'm going to call this logic and memory cell, just to disambiguate it from the logic in memory efforts that have been, that are traditionally done, where logic structures look very different, memory structures look very different, and logic and memory are brought closer to each other, and that helps overcome some communication overheads and give some performance benefits. So this is not really bringing logic and memory close. This is merging logic and memory. It's overlapping logic with memory. So what can this really mean? And if I wanted to say very safe things, then probably it could mean some smart memories and smart read heads. But something more daring would be the possibility that logic within memory could give you the capability of performing computation within the memory cell. Now, that is also aligned with this interest in trying to build these memories which have their search capabilities and sorting capabilities. So that does seem like something which is useful in general for memories. But even beyond that, if it can do some more general purpose computation, having processing capability is not bad at all. So, and that could also mean less delay and power. And basically, it could not go as far as computation where data is stored. There could be a general, instead of a hard drive that is also doing computation. It could be close to where data is stored. So that could be a little bit of exaggeration, but it's a possible direction that this could go in. The other really nice thing about this is the parallelism that happens because of this. So for, let's say, a 1 megabit MRAM array, what we have are potential 1 megabit by 3 logic gates over there, if you want to consider that 2 of them are operands, and not every device can be a logic gate. So you potentially have that many NAND gates inside this MRAM array. So the parallelism that could come out of it, it depends on the amount of memory available. But that's just NAND operation. And so let me conclude with saying that MTJs are excellent memory devices, and we'll hear a lot about them in this workshop. But they can also perform logic operations, and therefore, possibly together, they could bring more performance or more functionality than individually.
So we work on comments and questions.
Mm-hmm.
Could you repeat the question for the webcast?
Can one switch to 0 accidentally without being programmed?
So your question is, can these be switched from one state to another without being programmed?
Not the possible sources of errors.
Oh, possible sources of errors. Well, I guess errors will come from variability. Errors will come from different threshold currents, from different supply voltages, even how the voltages are being supplied. If they are coming through this complex circuitry, then noise in that particular circuitry. So yes, errors are definitely present. They're definitely a big issue. But as we are scaling down devices, errors and reliability is one of the major issues that everyone has to deal with. So I'm hoping that when MRAM devices issues are figured out, some of these are also addressed in some way.
And also another question is, the time it takes to switch these devices compared with the normal time of computing, are they comparable, or is one slower than the other?
Right, so the question is the time of switching of the devices, is that comparable with normal electronic switching? So as of now, magnetic tunnel junctions take larger time than electronic circuits. I mean, I would say the delay of a CMOS gate is about 10 plus picoseconds, and MTJs definitely take longer. With the devices that we had, it took sub 1 nanosecond delay. So the recent devices that were fabricated at the U of M, they took around 560 picoseconds. So it can be within the 1 nanosecond bracket. But what I see this is, data does not need to come into this special processing unit and then have to be written back. It can be done right where this whole data is present. So that avoidance of having to come through all these layers and going back, that could potentially be much quicker than it would be in an electronic setup. So that's a possibility, that it would be faster.
All right, thank you. So time is up. Let's go discussions offline. So let's move to the next session, next speaker. So next speaker will be Jashuyan from HP. The title will be Recent Progress on Oxide-based Memory Resistive Device in HP. So, please welcome, Josh.
Okay, so we got your PowerPoint. Just go ahead and full screen it, and I'll match the screen.
I'm sorry? Okay. Okay, good morning. Thank you for the chairman. I'm Joshua Yang from HP Labs. I'm going to switch the gear in my talk. The device I'm going to tell you have nothing to do with the magnetic property. The switching property of the device is just from the oxide material itself. I myself is a material science guy, but I will try to not talk too much about materials detail, but focus on the device level, talking about recent progresses on oxide-based memristive device in HP Labs. I will first give a very brief introduction, mainly talking about the recent two demonstrations of the applications on magnetic on memristive device, and then I will briefly touch on the working mechanism of the device, and based on the working mechanism, family of nano devices we built in our labs, and then I will talk about the challenges and the solutions. First, what does the device look like? Here you are looking at 17 cross-point devices. At each cross-point there is one memristive device, and the cross-section of the device looks like this. You have the bottom metal electrode and the top metal electrode. In the middle, you have an oxide material. The oxide material itself is a wide bandgap semiconductor. And inside the oxide, there are a lot of oxygen atoms missing, leaving a lot of oxygen vacancies. Oxygen vacancies can serve as an untapped dopant to dope the oxide semiconductor material. And different from the dopant in silicon, such as boron, here the oxide vacancy dopant can actually be moved by electric field. So you have a metal semiconductor interface. It can be a non-ohmic contact, such as you can think about a Schottky-like contact here, but the oxygen vacancies can be driven by the electric field to move to one of these interfaces to reduce the electronic barrier there, so give you a low resistance state of the device. The oxygen vacancy at the interface region can be moved away from this interface and give you a high resistance state of the device. That's why the device can respond to an electric field and changing the resistance. If you put these individual devices into an array, you get this crossbar structure. Here you are looking at a 1,000 memristive device within a 2 micrometer by 2 micrometer area. And the crossbar structure has these proposed applications. The obvious one is non-volatile RAM, and the resistance change of the device is continuous from a low resistance to a high resistance value. So that's why it can also be used for analog circuits, such as neuromorphic computing. There are two more new application demonstrations called hybrid circuit and logic circuit recently. I'm going to talk about these two applications in the next few slides. First, the hybrid circuit. It is related to FPGA type application. We know an FPGA type chip usually has one issue is that most of the chip area is not occupied by the CMOS device. Rather, it is actually occupied by the wires, connections. And if we can lift the wires and the connections from this CMOS layer and put it into another layer on top of the CMOS layer, so we can put more devices in the CMOS chip, and then we can use tungsten vias to connect these two layers. So here we use a memristive layer to serve as the wires and the connections. And in this case, the device, you will have a higher device density, and also device can be operated at a higher speed and also consume less power. This is the CMOS chip. This is the CMOS chip with the Memristive layer on top of that. These are the VS. So these are the electrical measurement results from the hybrid circuit we built. And by switching the Memristive device on and off, we can reconfigure the connection patterns of the CMOS devices, so giving us many different logic operations. This is the second application I'm going to talk about for computation. In addition to a natural memory application, Memristive device can also be used for computation by using the so-called mature implication, which is the fourth fundamental logical operation in addition to OR and NOT. By using two Memristive devices in the array, you can realize the implication logic. We demonstrated that use three Memristive in a row, we can realize the NAND operation. These are the electrical measurement results showing the truth table of NAND from three Memristive in a row. And we know NAND is a universal logic based on which we can build any other logical operation. Compared to the traditional logic, this implication logic has a smaller footprint and it is non-volatile. Okay, what is the working mechanism of the device? I have talked a little about the working mechanism of the device. Here you are looking at the typical IV switching loops from a micron-sized device and a nano-sized device. The nano-sized device need a smaller current here, and you can see for this device you use a negative voltage. You can change the device state to from a high resistance state to a low one. Then you get device in the on state, as shown by the green IV. And you can reverse the voltage polarity. You change it to the high resistance state, as shown by the purple IV in the off state. So this off state is showing a rectifying IV, reflecting the metal semiconductor contact. It's like a Shackle-like contact. Okay, so without going into the detail showing the evidence, I'm just going to summarize the switching mechanism for this device. First, it happens at the interface region. Oxygen vacancies are responsible for the switching. And it is localized inside of the device rather than uniform across the entire device area. You can imagine there is a conductance channel inside of the device made of suboxide material with a lot of oxygen vacancies. Oxygen vacancy can be driven up and down, giving you the switching. Okay, based on this switching mechanism, we can really fabricate a family of nano devices using this very simple metal insulating metal structure. Whenever you have this metal insulating metal tri-layer structure, you have two interfaces to play with. So each interface can be either ohmic or Shackle-like, depends on the oxygen content at their interface. So this gives us 4 combinations, as shown here. Each combination has its own IV characteristic. For example, for this one, you have no vacancy at the top interface, but a lot of oxygen vacancy at the bottom interface. If you ground the bottom interface, you will get a rectifying IV like that. If you reverse the oxygen vacancy profile by having no vacancy at the bottom, many vacancy at the top, then you get a reverse IV characteristic. If you have vacancies at both interface, then you get a very conductive IV. If you have no vacancy at neither interface, you will have a head-to-head diode, very resistive and symmetrical IV. The beautiful thing about this is you can change the device resistance by using a voltage from among these states. For example, this is electrical measured data from a nano device showing the switching between these two states. And this is electrical measured data from a nano device showing the switching between these two states. As you can see, it's like a diode changing its rectifying direction. And this is metadata showing the switching between these two states. You really have a family of nano devices just based on very simple device structure. Okay, now I'm going to focus on the challenges and solutions. Traditionally, these kind of devices are very strong in this list. It has a great scalability and very fast switching speed, non-volatility, and it has a potential for multi-level cell, and it can be stacked up for many, many layers, giving us a very high-dense 3D structure, and it has a great CMOS compatibility and low cost. But it also traditionally is weak in this list, including the endurance, how many cycles it can switch, device yield, operation energy, electron forming issue, and the integration. I'm going to talk about these one by one in the next few slides. First, the challenge endurance. About 3 years ago, we use a titanium platinum mature system, and normally we get 10,000 switching cycles from the device. Then we replace the titanium oxide by tantalum oxide mature. About 2 years ago, we get improve the endurance by 10 times, and we further improve the device structure by changing the materials, and we get easily over 10 billion switching cycles from the device. Actually, after 15 billion switching cycles, the device is still switchable, it's still functioning. It just takes longer to get a higher endurance measurement. So as you can see here, mature system play an important role in the endurance property. So what are the criteria for mature selection? As I said, in the switching device, you have a conductance channel. It's a suboxide surrounding by a stoichiometric insulating oxide serve as the matrix. So the first criterion is that these two mature systems need to be in thermodynamic equilibrium, meaning these two materials, the channel material and the matrix, should not react even at high temperature induced by the Joule heating inside the device. And the second criteria is that the channel material need to have a large, mobile species solubility so that it can accommodate the mobile species during switching, so it will not lose these species even after billion switching cycles. Titanium oxide material is a system does not meet the criteria, and it has a poor endurance. But tantalum oxide is a mature system and meets these criteria very well, and it has a great endurance. Okay, device yield. Traditionally, the device yield is low, few percent to less than 50%. Obviously, you need to improve that. We found that the key for the yield is to control the formation of the switching channel inside of the device. One approach is to planting seed of switching centers by thermal diffusion, as shown here. We use titanium adhesion material to thermal diffuse through the platinum bottom electrode. It diffuses through the ground boundary, form very little atom chain, and get to this interface, react with the oxide material, locally reduce oxide material, giving us very small switching center seed we need for the conductance channel formation. And by using this approach, we fabricated devices showing almost 100% device yield and a very small variance from device to device, from switching cycle to switching cycle. Operation energy, since we are talking about making the device extremely small and very high density chip, so the individual device need to consume as little as possible energy. In optimizing the material system, we achieved less than 5 microamp switching current. It corresponds to about 0.1 peak joule energy. And surprisingly, the device still has a very large on-off resistance ratio. The electrical forming issue. Electrical forming process is an extra step we needed to use as a prepared device to precondition the device from an unswitchable state to a switchable state. It consumes a lot of power and high voltage, so it needs to be removed. The electrical forming step is shown as the red IV here. You can see it needs a huge voltage, and it causes dramatic changes in the device, even damage the device. So it needs to be eliminated. But how? In order to do that, we need to understand the mechanism. And we found that the electrical forming have done nothing but just create a conductance channel of suboxide material in the stoichiometric oxide. So if we can build the suboxide channel inside of the device in the fabrication process, by doing this, we can probably remove the electrical forming step. And we show this, the electrical forming step is red IV. It's almost identical to the subsequent normal switching as shown by the purple IV. In other words, in this kind of device, we do not need electrical forming. Okay, to make a device in the lab is totally different from making a device in the fab at large scale. So here, Janice is holding our first 12-inch wafer with Memristive device. And if you look at this device, the cross-section TEM, you can see if we cut along the top electrode, cut along the bottom electrode. So these are the switching IV from this device. Basically, we show here, even by using the industry standard process, we can make this device at large scale. Okay, have we solved all the problem? Not yet. And as you can see, we use different solutions to deal with the different challenges. What we really need is to have one solution that can solve all the problem together. So we are not there yet, but I think we are close. And to summarize what I said, I demonstrate that two new recent applications of the Memristive device is a hybrid circuit and a logic circuit. I briefly talking about the switching mechanism involves localized conductance channel at the interface region. It is oxygen vacancy drift responsible for the switching. Based on this mechanism, we can fabricate a family of nano devices with a very simple device structure. And in dealing with these challenges, we have achieved over 10 billion switching cycles from the device and about 100% device yield, less than 5 micron switching current. We get rid of the electroforming issue, and we demonstrated the first 12-inch wafer fabrication. Finally, I'd like to thank my coworkers, and Janice is sitting there, and others you may also recognize. And for those who are interested in the details, you can look at some references. Okay, thank you for your attention.
Thank you. Any questions, comments, please?
You created, if I understand this correctly, logic with the actual resistor structures. Have you considered using lookup tables and doing a hybrid structure that way for doing logic?
The question is, are we going to create a lookup table for the logical application? At this stage, we just demonstrated, the very basic operation and just a very fundamental 3 memristor. You can realize the NAND function. We haven't proceeded from here yet. This kind of question, actually, we are going to leave to the community such as this.
Yes, I have a question on slide 18, please. The bottom graph, could you comment, I have 2 questions. First of all, the data on the bottom graph. Did you perform a verify operation after every cycle to make sure that the resistance is reached for the on and off state?
Okay. The question is, did we verify after each switching event? So the answer is that we actually undersample the switching here, meaning we measure probably after every 0.5 million cycles because we cannot measure every data point after switching, and it's just too big. Even this has 20,000 data point here. It makes the PowerPoint very big. But anyway, so we didn't measure everyone, but from all the one we measured, it's about we do not find any error or unswitching event.
And my second question is, this data appears to be from a single cell. Do you have comparable data from large arrays, let's say a megabit sized arrays?
We don't. These are from the individual device now. Yeah.
What was the size of the device?
For this device specifically, it's very big, easy for the measure. It is about 100 micrometer diameter. But for others, these devices are 50 nanometer by 50 nanometer area.
Okay, so it's time to move it to next presentation. Thank you very much. So next presenter. So you are. Okay. So next presentation will be given by Arijit. Okay. So the 1T1 STT MTJ memory arrays for embedded applications. Arijit will give a presentation from Intel.
Thank you. Yeah, got it. So the title of my talk is the 1T1 STT-MTJ memory array for embedded applications. So this is kind of different from most of the non-volatile memory forums and application spaces that we look at. It's essentially for like off-chip memory that we talk about, non-volatile flash or even magnetic memory. So I'm going to take a stab at looking at something which we are which I think, apart from Intel, many other companies, industry and academia alike are looking at, which is essentially to study this kind of memories for embedded applications, for very high density on-chip memory. And I'll present some of our thoughts from a circuit designer's perspective. That's what I am. So I'll start with a basic introduction of the 1T1 STT-MTJ cell. And thanks to my previous speaker, this has already been introduced, so I'll quickly go through it. I'll present some of the basics of the macro models and micro models, which are being studied and verified with experiments, and which give us some kind of a confidence in believing that the projections that we are trying to make are kind of correct. I'll take you through a model study on a 22 nanometer process technology estimate, like the transistor models or estimated models. And I'll talk about the different kinds of failure mechanisms, which will, I think, answer one of the questions from the first talk. What are the different kinds of failure mechanisms we can think about in this kind of structures? And again, looking at it from an embedded memory perspective. And finally, I'll talk about some of the issues with thermal stability, since we are looking at extremely small dimensions. And look at some alternative structures and what are the problems and potential solutions. And there are no solutions for many of the problems as of yet, so I'll talk about those as well. So this is a traditional graph which shows on-die memory. So this is the last level of cache, let's say. And on the y-axis on this side, I have the added density, and on this side, I have the cell size. And I have process technology node all the way from 90 nanometer to, let's say, an 8 nanometer process. These are data points from different industry standard leading edge processes, and we see that we have pretty much been on the curve for both SRAMs and embedded DRAMs. So the red one is for SRAM, the black ones are for embedded DRAM, and we see that and these two lines are essentially for the cell size. So the cell size keeps on decreasing, whereas the array density keeps on increasing. If you look at the F squared size of the cell, which is typically in the order of 48 to 56 F squared for SRAMs, around 10 to 16 F squared for DRAMs, embedded DRAMs. And these are essentially large numbers. If you're looking at like several GBs of storage on die, these are large numbers, and it's not even very clear how we can achieve these numbers at very scaled technology generations. So if you think about SRAMs, we started with a bunch of circuit assist techniques to help the scalability of SRAM. We started with sleep devices, with read assist, with write assist, and now we are moving to there are certain levels of the cache which need the 80 cell, which is a variant of this traditional 60 transistor SRAM. And further onwards, this will become more and more difficult. So it becomes kind of imperative to look at other kinds of structures, other kinds of memory solutions which are out there, and potentially identify a solution. So if I look at the different kinds of emerging memory technologies, we already have the SRAM and DRAM. We know how these are built, and we will continue to build these structures. But apart from that, if you look ahead, we have MRAMs, we have flash NAR, we have PCRAM, we have ferroelectric RAMs, and different kinds of technology solutions, which can give us cell sizes which are pretty small, 6 to 10 f squared. We are looking at read-write speeds in the order of tens of nanoseconds, which is an order of magnitude almost slower than an SRAM, but we believe that it is okay for embedded applications, especially as a low-level cache. And finally, endurance numbers. We know that SRAMs and DRAMs endurances are extremely high, whereas some of these memory technologies have limited endurance, so that's something to think about, especially when it's used in embedded applications. So the STT-MTJ, which is a spin torque transfer magnetic tunneling junction cell, the chief advantages would be it is process and voltage compatible with CMOS. We can potentially make it work at around 1 volts, which is a big thing. So that's, I think, one of the game changers for this particular technology. It can potentially give us very high density, especially when you're comparing it with SRAMs or embedded DRAMs. Nanoseconds read and write speeds, which is, again, very attractive as a circuit designer. And finally, it is non-volatile with long endurance. And as we already saw, we can take it one step further and think about embedding non-volatile elements in latches, flip-flops, and so on and so forth, to give you more kinds of flexibility in designing in microprocessors or signal processors, whatever it may be. So these are some of the published data from typically from ISSCC, IDM, and VLSI conferences that we have put together all the way from 2000 to 2012. And we see the different cell sizes and the different array sizes. And you can see that as time has progressed, we can now achieve sufficiently large arrays. There were publications from TSMC and Toshiba with array sizes as high as 64 MB, a huge amount of memory to show as a proof of concept. And also the cell sizes are pretty small, 0.1 micrometer squared, where we are at the moment. So going forward, it looks promising. So there is interesting work going on, and it looks like this is a potential dense memory solution. A brief introduction to how it works. So we have 2 magnetic layers. One is called a fixed layer because it has more magnetic energy. So you can think about it that way. The other is a free layer, which is a thinner layer, which has less magnetic energy, and it can be switched. And there is an interface material which is traditionally MGO. MGO is traditionally used because it also acts as like a spin filter. So without going into the details of it, there are 2 potential states of this structure. One is the parallel state where the 2 magnetization vectors are pointing in the same direction. It gives you small resistance. The other is the anti-parallel state where the 2 layers are pointing in opposite directions, giving you a large resistive state. These are all in-plane magnets, and the current is flowing perpendicular to the magnet, so it's flowing in this direction. So how do we change state from one to another? So when we want to change state from, let's say, the anti-parallel to the parallel direction, so the anti-parallel to the parallel direction, electron current flows in this direction from the fixed layer to the free layer. As a result, it carries, like when the electron current flows through this fixed layer, the spin in the fixed layer polarizes the electron, the spin of the electron, and as it propagates to the free layer, it exerts a torque on the free layer. And this torque on the free layer is what causes the magnetization in the free layer to flip. And thus we go from an anti-parallel to a parallel state. Very similarly, when electron current is made to flow in the opposite direction, some of the upspin currents in this case reflect back, whereas the downspin would go this way. And it will eventually cause, again, a torque on the free layer, and the free layer will flip, which will give you parallel to anti-parallel configuration. So this is how we can switch from parallel to anti-parallel versus anti-parallel to parallel. We go from low resistance to high resistance. So from a material choice perspective, there are three important factors that one needs to consider. The first is the TMR. The TMR is the tunneling magnetoresistance, which is defined typically as the delta R, the difference between the two resistance states, divided by the smaller of the resistances, the R parallel, and which typically say 100%, or like it's expressed as a percentage. So a TMR of 200% would essentially mean that the R high is 3 times that of R low. Then we have the RA product, which will essentially be the resistance multiplied by the area. It gives you the input impedance of this device. And finally, JC0 is the critical current densities which are required to switch the free layer magnet. So how do we use it in a typical cell? The typical bit cell would look like this. We have a transistor which acts as a selector device with a memory element, which is the STT-MTJ in our case. The right is bidirectional. As I already mentioned, the current needs to flow from parallel to anti-parallel and again from anti-parallel to parallel to give us the switching from one state to another. So the right is bidirectional. So we need to play around with the source line voltages and the bit line voltages appropriately so that we can get bidirectional right currents. The read, however, is done typically in one direction. And there is a lot of argument of whether the read has to be in this direction or this direction. I can talk about it in details offline. But let's, for the sake of argument at the moment, assume that the read is done in this direction. And we are essentially looking at extremely small cells. So let's say we are typically, hypothetically looking at a 6F squared or an 8F squared cell, where the MTJ would be around 2F by F. So it's a 2F squared MTJ only size. So I'll just have one slide on the typical modeling approaches that people use, and you can go into the details of it. And there is a vast amount of literature on this. So one of the approaches is essentially an analytical approach, and it matches pretty well with experimental data, as you can see for different kinds of critical current densities. So on this x-axis, I have what is the critical current density, and this is the right time or the switching time. So the critical current density, as it scales down, the right time increases almost exponentially here. It increases as 1 over tau, kind of. It rapidly increases. So this is for 3 different JC knots, or critical current densities. The important thing to remember here is that most of the write times are limited in this graph, at least between 1 and 10 nanoseconds. So it's a reasonable assumption to make that switching times in these devices would be in the order of 10 nanoseconds or around 10 nanoseconds. Very difficult to get it below 1 nanosecond because of a whole lot of physics involved in this. So we are not looking at something which will be like a drop-in replacement for SRAM. It's going to be much slower than SRAM for sure. Also, there is another approach for modeling typically, which also gives very good measure. This is an atomistic approach which has been pioneered by so many university researchers. It involves solving both a transport equation with LLG. LLG is the typical magnetics dynamics equation that is used. So by coupling transport with dynamics, we can get very good estimates of resistance versus voltage, of the torque exerted on the free layer, and so on and so forth. This is a typical graph which shows the resistance on the y-axis, the voltage applied on the x-axis, and we see that we can get very good match with measured data using this atomistic approach. So whatever the modeling approach may be, let me briefly go through what are the different kinds of failure mechanisms we can think about in these structures. So the first is read. How do we read the cell? We read the cell by allowing a capacitor on the bit line to slightly discharge through the cell, and we look at the voltage of the bit line. So it's a typical read scenario. So as far as read is concerned, so we should have. This is a Monte Carlo simulation showing the two different distributions for read current. This is the lower of the read currents. The blue one is the higher of the read currents. And we have failure modes which are shown here. So the first is the sense-limited failure, which means that in the given amount of time that we need to read, we could not distinguish between a high state and a low state. So that gives us one of the failure mechanisms, which is a distinguishability failure. Then we also have something which is called the read disturb failure, which means that in the process of reading the cell, you can inadvertently write into the cell. You can flip the cell. So this is another disturb mechanism which comes very much from SRAM. It's called the read disturb mechanism. And finally, we also have some time-limited read failure mechanisms, which essentially means that if you wait longer, you can potentially resolve the two states, but since you haven't given it enough time, it could not resolve those two states. So this is more like a time-limited failure, and it can be potentially solved by slowing down the clock frequency. Looking at the read failure mechanism, so what the read failure does is it constrains the material design space in the TMR and the RA product space. So if I draw the TMR on the y-axis and the RA product on the x-axis and look at different kinds of contour plots of iso probability of failure, we can, from the read disturb mechanism, find out. So these are essentially 6 sigma plots. We can find out what is an allowed space. So in this particular case, this blue line is essentially what is allowed. So the TMR and the RA product needs to be in this space for us to be able to use it as an embedded memory solution. Moving on from read, the next one is write. So when does write failure happen in this memory? The write failure happens when the current that passes through the cell is not high enough. It's not greater than the critical current, right? So you have to meet at least the critical current density in the cell in order to make the transition. So let's say we look at, again, a Monte Carlo distribution of write. So this is the red curve is one of the write current distributions. This is the other write current distribution. And the critical current distributions are shown in this black dotted line. And we see that in these cases, in these particular occurrences, the write current has been lower than the critical current, which means that we will not be able to write into the cell. So this is a write failure mechanism that we need to worry about. And as with read, it also constrains the material design space. What it constrains is the RA product versus JC material design space. And we can again draw very typical contour plots to show what the probability of failure is. And here, this area would be the area which is permissible. So we need to have an RA product and a JC knot combination, which falls in this area for us to have a dense cell. Finally, if I take the read and the write together and plot it together, we can have a typical plot where we can plot the TMR, the RA product, and the JC. And we see that there are certain devices. So this blue and the blue area and the red areas are the ones where we need to be in order for us to have both successful reads and writes. And we see that there's typical cells, single barrier cells, double barrier cells, different kinds of cell configurations, which fall into this category and into this area, and which essentially tells us that some of the material design specs that we already have are pretty good for meeting embedded applications. And there is a lot of work going on in making them better. But it's already pretty good in terms of where as a circuit designer we would like these to be. And just as a side note, we can relax a little bit of this material design space if we have a larger cell. So there are circuit assist techniques like word line boosting or having a larger cell, which can potentially give us some benefits and expand the material design space a little bit further and give us more flexibility. So I don't want to go into the details of it, but again, there's a vast amount of literature on this subject as well. Finally, thermal stability. So this is something which has been a problem with the hard disk industry for a long time, if I understand right. And we will see the same problems in embedded applications once we go through a very small dimensions. So these are some thermal stability numbers. So what kind of energies in the magnet are we looking at so that we get enough thermal stability for a 10-year or a 7-year lifetime? So this is what these complicated graphs are essentially trying to show us. So let me go through the graph a little more carefully. I think this will be of interest to people of not only design, like circuit designers, but material designers, architects, everybody alike. So on this particular graph on the left side, I have the line failure probability on the x-axis. The line failure probability is the probability of having a failure when we are trying to read a particular line in the array. So for a 256 MB array or a 256 MB array, let me look at a 256-bit read or a 512-bit read. So we are reading 512 bits together or 256 bits together. And we see that the line failure probability is constrained in a very narrow space for a particular DPM yield and everything put together. So it's constrained in a very narrow region at around 1e minus 11. And if this is what we want, then we see that in terms of KT, what's the total energy of the magnet that needs to be there, we are looking at something in the order of 50 to 52 KT. So we are looking at, in this region, of more than 50 KT of stored energy in the magnet. I can translate that into another plot where I have the memory size on the x-axis and the KT required. This is a very typical terminology for how much energy you would store in the magnet for you to be able to get enough yield. So what's the KT requirement on the y-axis, and I have memory sizes on the x-axis. We see that it's more or less independent of memory. It's not that if you go to a really large memory, you need a lot more storage energy, or you can trade it off very easily. So it seems like more or less all the way from 64 MB to 512 MB, no matter whether you do 2-bit ECC or 1-bit ECC or no ECC. If you do like no ECC, you can get like a little bit of advantage, but the advantage is not much. So I personally believe that whatever we do in terms of redundancy in these arrays or even in design, we are potentially looking at thermal stabilities which are in the order of 50 to 60 kT for small dimensions, which I think is will be a real problem, will be a real challenge if you are really looking at very small dimensions. Finally, there are different kinds of MTJs. Again, a lot of literature on each of these. So these are different material stacks that people use. So the one that I talked about has a single fixed layer versus a free layer. There are other structures where you have one fixed layer, two fixed layers, and one free layer in between, which is called a dual barrier. So you have two barriers. This helps in writing the cell, so it has better writability. So if I write a table, so this guy will have a better writability. This is another structure which is called, where the free layer has been replaced by what is called a synthetic antiferromagnet. So this also has good writability. And finally, we have a dual barrier with a synthetic antiferromagnet. This has very good writability. Readability, this one has the best readability. This is not very readable with dual barrier structures because you tend to lose a lot of the TMR. Again, without going into the details of it, if I look at the table, the readability of this guy would be high. And finally, in terms of thermal stability, anything to do with synthetic antiferromagnets can potentially solve our problem of stability. So the synthetic antiferromagnet kind of free layers make most sense when we are concerned about stability. So this is a gist of the different kinds of trade-offs between read, write, and stability for different kind of stacks. And depending on the application, whether we need real fast read or fast write or really a dense array, one or a combination of two or more of these would be the right solution from a materials perspective. Finally, a brief summary. I talked about this 1T1 STT MTJ being a potential successor to SRAM for high density. The reduction of JC0, which is a critical current, is required for getting denser cells. I think that's one of the things that one needs to look at from a materials design perspective. And unless we do that, it's very difficult to get something which will be 4 or 5x smaller than an SRAM, which is kind of where we are in dense memory solutions. Finally, the material design space can be relaxed by using a bigger cell, but that's not a trade-off that circuit designers would want to do. Thermal stability, I believe, will be a big problem once we go into smaller dimensions, 50 nanometer and so on. So more work needs to be done in the material space to give us thermal stability of these bits without ruining the read or the writability. Finally, there are alternative structures. Some of this I showed, which can allow the non-volatile nature of the memory structures to persist. But these are, again, work in progress, and there is a lot of work going on. And the trade-offs between read, write, and stability needs to be quantified before we can move to these alternative structures. So thank you.
I think we have time for just one question, please.
Sure. Oh, the bit error rate? So the way this works in this particular case, the way it is constructed is, what we do is you start with an yield number. So you have a wafer, you have so many dies, we start with a yield. So from that yield number, we can project what needs to be the line failure probability for us to get to meet that yield requirement. That's what is shown here. So this is the line failure probability. So from that line failure probability, so you can think about the line failure probability as equivalent to a bit error rate. But it's not the raw bit error rate. It depends on how many bits you're reading at a time. So it's the line failure or the line rate. You can call it the line rate. So we are looking at something in this order, 1e minus 11 as the probability of failure for a line. That's the one without any ECC. So if you have ECC, you can relax it a little bit. Oh, I think this. This was. This is sec-dead. This is dec-dead, and I think the length was on 128 bits at a time. So it's the chunk is 128 bits. Yeah.
Okay. Thank you to the speakers. Okay. So we're moving to the last presentation of the session. Dr. Alexander Dorothy from Grandis. The paper will be latest advanced is in STT-RAM.
Thanks for the introduction. Well, I think we're running a little bit late on time, but the last two of the previous talks were very good introductions on STT-RAM, so I can skip through some of the introductory stuff here, hopefully. But I'm here to talk about the latest advances in STT-RAM, which is the memory based on spin transfer torque. A little bit different from the logic that the first speaker in this session was talking about, but very similar to what the previous speaker from Intel was talking about. I'm going to focus mainly on the device side, the latest advances on the devices, and also in terms of the chip development. So I'll try and go through the introduction very quickly. I want to spend most of the time on these aspects, some of the latest advances that we made in the last year on both the materials and the chip. This partial perpendicular anisotropy, the latest results from these dual MTJs that the previous speaker was talking about, some results from our DARPA STT-RAM program, especially this Hynix Grandis 64 megabit STT-RAM chip, and then looking into the future on some of the perpendicular MTJs. So I think I don't want to go through all this, but I think that the main point is that a lot of new technologies are emerging, and a lot of the existing technologies are having increasing difficulty scaling. And as the keynote speaker this morning was alluding, that really there's an interest in finding a non-volatile, high-density memory that's fast and scalable. I think it can really, if you have such a memory that has low power consumption, you can really address these two critical areas, both mobile and data center applications. You can really dramatically reduce the power consumption if you have a fast, non-volatile memory. And interestingly, you can also change the whole architecture of these systems as well. This is the STT-RAM cell that the previous couple of speakers were mentioning. It's based on having this MTJ element here, which stores the data, and then you write it one direction or the other in order to write the two different states. And these are the characteristics. The MTJ is the same MTJ that you have in every single read head in a disk drive, except in this case it has to be stable, thermally stable, so you can retain data rather than just use it as a read sensor. But this memory has all these characteristics. It's non-volatile, highly scalable, low power consumption, fast read and write speed, although if you want to get down to true SRAM speed, you have to drive it with higher current. Essentially unlimited endurance, and can be high density in a standalone application. I should also add, based on the first talk, it's actually there's no arrays needed at all. It's simply you write a 1 or you write a 0. No array cycle needed. So Professor Burak should be pleased about that. Also random access. I won't go through this, but this is a traditional MRAM cell and an STT-RAM cell. It's essentially a simpler architecture because you don't need this additional line here, the right word line, in order to create the field to switch the bits. We're not using magnetic fields in STT-RAM. We're using a spin polarized current going through the cell in order to switch it. And then I think the key difference also compared with a conventional MRAM cell is the scalability. If you look at conventional MRAM, which was a very hot topic a few years ago, and there were some MRAM cells in commercial production these days up to about 16 megabits. But the problem is when you scale MRAM below about 100 nanometers, that the current you need in order to switch the cells, create enough magnetic field, it rises up quite fast. And essentially, it's not scalable below about 100 nanometers or so. Whereas with STT-RAM, the right current you need in order to switch the cells, it reduces as you reduce the cell size. It's proportional essentially to the area. Perhaps I should also mention the whole the spin torque effect that was actually is another one of those technologies that came out of IBM originally. It was invented it was theoretically predicted back in 1995 by somebody called John Slonzewski. And then here we are about 15 years later, and we're finally getting close to getting into a commercial chip. This is the point about scalability. So essentially, the write current you need to drive these devices scales down linearly with the device area. So if you have a device, say it's about 90 nanometers, that would be an area here, and the write current for a 90 nanometer device is about 150 to 200 microamps. But when you scale it down to, say, a 40 nanometer device, which is this bottom data point here, then your write current reduces to around 40 microamps. So essentially, it follows the area of the device. And because it goes down as area, not linearly, it gets better as you scale it down. So this graph shows typical write current density for MTJ is about 1 megaamp per centimeter squared, or 1 to 2. And as you scale down the technology node, this is the write current you need in order to drive the cell. And then the shaded in green here is the available current from a minimum cell size transistor with just a 1F gate width. And that scales down linearly with the gate width. And so there's actually a crossover point here around 45 or 32 nanometers where you have enough current to drive the cell with the minimum possible transistor size. So the result of that is it means you can pack this into a 6F squared cell beyond about the 30 nanometer node. Here's how you arrange a 6F squared cell. You share the source line. You have the MTJ up here between two of the metal levels. And essentially it's 3F by 2F, 6F squared. It is actually possible to go further than that. If you had a vertical transistor, which is out on the roadmap for future DRAMs, if you combine a vertical transistor with a MTJ with the magnetization in the perpendicular direction, you can actually pack this into a 4F squared cell. And potentially in the future, you can also go to multi-level cells, but that's further in the future. So this graph shows or summarizes some of the chip development that we've been doing with our partners over the last 2 or 3 years. The graph or the images on the left are from a Renesas chip at 90 nanometers back from 2008, and the ones on the right are from a Hynix chip that we developed with them at 54 nanometers, and we showed this at IEDM conference a couple of months ago. So they're similar, but with a few key differences. In the case of Renesas, the MTJ is placed up here between metal 3 and metal 4. So up there, the design rules aren't quite so tight, and therefore the cell size is bigger. But in the case of Hynix, they want the tightest possible cell size. So they place the MTJ right down here between the metal 0 and metal 1 levels. So with the Hynix case, we got down to a cell size of 14F squared, which is the smallest to date, I believe, with an STT-RAM chip. Some of the other advances that I'm going to talk about in the next couple of slides, these are really key from the materials side. I just summarized them here. One is this very low write energy that we demonstrated a little under a year ago through our DARPA project with various universities. This is very important for showing that the write energy does become low as you go to very fast write speeds. And the other interesting or big advance is these advanced dual MTJ devices that now reach a TMR of over 150%, and I'll show a graph on that a little later. So one of the challenges we've had over the last sort of 5 to 10 years is how do you reduce the write current on these MTJs sufficiently so that you can switch them with a small transistor, and then at the same time, how do you maintain the thermal stability? The previous speaker was talking about thermal stability. Because the problem is that the things you need to do in order to reduce current all appear in the thermal stability equation as well. So if you try and reduce one, you normally end up reducing the other. So that's been the big challenge. But on the next page here is I wanted to show this partial perpendicular anisotropy effect. This has been one of the key advances that has allowed us to kind of separate those two things. And the way it works is you introduce through free layer or capping engineering in the MTJ, you can introduce this partial perpendicular term, which cancels out the demagnetization field here in this equation for the switching current. And so you can reduce the energy barrier for the switching substantially, while still maintaining the thermal stability at rest. So what this graph is showing here is the amount of this partial perpendicular anisotropy is a percentage of HD here, and for different free layer thicknesses. And I think a year ago I showed these two lines here. But the big advance has been in the last year in achieving these high levels of partial perpendicular anisotropy, even at free layer thicknesses right up to 4 nanometers. And it involves free layer engineering and so on. And the reason why it's so important is because as you scale down these devices, they become smaller. You lose the thermal stability unless you can increase the volume of the free layer. And if it's becoming smaller, the only way to increase volume is to make it thicker. And so if you have a 4 nanometer, for example, or 3 to 4 nanometer free layer, but with a high partial perpendicular anisotropy, you can have a low switching current, but also high thermal stability, even beyond 20 nanometers. This is the other advance from the last year or so. It's a dual MTJ device, which for the first time we managed to achieve TMRs above 150%. So this is very important because one of the, I think the previous speaker was mentioning it, when you have a dual MTJ device, typically it helps a lot with the switching current, but you typically lose this TMR signal because you get some cancellation. But by engineering the free layer and the two barriers, you can actually maintain that signal in the device. So this is going to be very important in the future. You get a combination of a high signal and a low right current density in the same device. This one I think I won't go through in detail, but this is the progress. It shows the progress that's been made in these devices. There's the traditional bottom MTJ device with just one barrier. When you go to the high partial perpendicular anisotropy, you get to the blue line, you reduce the right current density to 1 to 2, and then with a dual MTJ device, which also has high partial perpendicular anisotropy, you can get down to around 1 to 1.5 in the right current density, and that's in megaamps per centimeter squared. This is the results from the DARPA program. We have a DARPA program funded by the government that involves a lot of universities, University of Virginia, Alabama, and a few others. And these are the goals of the program. We met the phase 1 goals last year, and the phase 2 will be due next year. But one of the big goals is to reduce this right energy. And the goal in phase 1 was to get below 0.25 picojoules per bit, and then next year we have to get down to 0.06 picojoules per bit. And these are done at a very fast read and write speeds, 5 nanoseconds per bit. And you can see a graph here of the right energy against the pulse width, and you can see from about 15 nanoseconds and below, the right energy is below this target threshold of 0.25 picojoules. In fact, the lowest is here at around 5 nanoseconds or thereabouts, about 0.16 picojoules. So this is the Hynix chip that we showed a couple of months ago at IEDM. I showed this already. This is the integration of the chip. It's a 14F squared chip, 2 transistors per unit cell. The size of the MTJ is 54 by 108 nanometers, and it's a 64 megabit chip. This is a graph of an optical micrograph of the chip from above. So the things I wanted to point out are the switching current, the switching voltage, and the resistance and switching current distributions. So this is across a whole wafer. This is the right current here in the positive direction, so going from the 0 to 1, and the right current in the negative direction going from 1 to 0, or maybe the other way around. But essentially, you get a current of around 100 microamps in this case, a little bit above the target, which is 60 to 80 microamps. Then this is the red is for a 54 by 108 nanometer device. So the goal is to get this a little bit further. This was from a bottom MTJ device. We're not using the dual MTJ devices yet in this data. And the other thing to point out is the switching voltage, which is about 0.6 volts and 0.7 volts in the two directions. Again, that's a little bit higher than expected. So once we go to the dual MTJ device with Hynix, this should come down by a factor of 2, and this will come down by close to a factor of 2 as well. So the net result of this is, if you just look at this resistance distribution from the chip on the right here, the green is the low resistance state, the red is the high resistance state. You can see not all of them are switching. It's about a 95% switching yield. So that's where we were in December. But I think within the next few months, hopefully in the second quarter, when we put the dual MTJ devices in this chip, this should go very high, above 99.9%. So I hope we can get fully functional chips from this process very, very soon. Here you can see a few devices shorted. So there's about 1% of those at the moment. Finally, just the other thing to point out is there are two types of MTJs you could put in an STT-RAM chip. One is this in-plane MTJ, where the magnetization is in the plane, and then here on the right is the perpendicular MTJ, which is the alternative way of doing it. Really, in the end, everything is going to go perpendicular. The question is when. Right now, the materials you need to create these perpendicular MTJs are not as advanced as in-plane. So the way we see it is that the in-plane will be commercialized first and will scale to a certain point, probably around 20 nanometers or a bit beyond, and then we'll switch to perpendicular. In principle, you can get lower switching current density from the perpendicular case. The issue right now is that the materials don't quite do that yet. And finally, I wanted to give a quick taste. So we're going to be presenting more on this at an IEEE memory workshop in May in Monterey. But we have a new structure for perpendicular, which has got some very interesting characteristics. A conventional, I think the previous speaker was mentioning that in order to get low right error rates, this is right error rate going down to about 10 to the minus 6 here. The problem is with this probabilistic type switching that you have in these MTJs, it's that in order to get to very low right error rates, you need to drive higher and higher currents through the MTJ in order to achieve that. But we have this, it's a very interesting structure, very novel structure that really dramatically cuts down on this right error rate, or the extra current you need to drive in order to achieve very low right error rate. So I'm going to be talking about this more in the next few months, but I just wanted to give a preview of it here because it's really quite a dramatic advance. At 10 to the minus 9 right error rate, that's assuming a 1-bit ECC, and you can see you get a greater than 5x improvement compared with a conventional perpendicular MTJ. I think I'll skip this one in the interests of time. This is where we see the technology compared with some of the existing technologies. Essentially, Hynix is working with us in order to try and create a DRAM replacement some years in the future. The issue is how do we get there? And one of the initial focuses is to create a 1 gigabit chip operating at about 10 to 20 nanoseconds with the goal of going for some mobile RAM applications. So you can get to, that's the target in the next year or so. Endurance is on the right here, endurance against write cycle time. You can see endurance is right up there with the working memories. And it is really quite a dramatic improvement in endurance and write cycle time compared with some of the flash and other technologies that are out there. This I'll go through quickly, but essentially, I think that the mobile applications are one of the near-term interesting areas for this technology, and that Hynix and others are interested in. You can replace not just some of the multi-chip packages where you have NAND and DDR-RAM in separate chips. You can replace them with STT-RAM in a single chip and have a chip that's non-volatile and fast, and also potentially cheaper once the yields reach the right level, because you only have one chip, and also cut down on the power consumption. The power you need to drive these chips compared with flash or DRAM, where you have it recycles all the time. The power consumption can come right down. So it's very interesting for these mobile applications. I think so. That would be one of the first applications. Another one here would be a little bit later because of the densities. You need to get up to maybe 4, 8 gigabits here to replace those ones. But then also, like the previous speaker mentioned, you can actually embed this memory into the same chip as a processor, as one of the lower level caches. And there you can really cut down on the cell size. So much space on a processor these days is taken up by SRAM, and you can really cut down on that area, as well as the power consumption by switching to STT-RAM. So I think you see those are three examples of some early applications. Finally, this is the last slide. So this is where I see the technology evolving. This is our roadmap compared with, I've got as a reference here the DRAM and the flash roadmaps. Right here today, we're working at 54 nanometers, 14F squared with Hynix. The next design is going to be probably, we might actually skip down to a 30 nanometer design at 8F squared. And there I think these mobile applications become interesting. It's probably going to be about 4 to 5 years before we can get down to a 6F squared and a DRAM compatible process. And then later on, once you get down below 20 nanometers, and you can get down to a 4f squared, the perpendicular MTJs will come in. So that's how we see things evolving, and I think this will go on the website after the conference. Everybody can take a look. So that's it. I think I'll leave it there. I think it's very interesting technology. There's been a lot of advances in the last year, and especially this Hynix chip. We're very close to getting it fully functional, so we're looking forward to sharing that with you soon. Thank you.
Questions, comments, please?
Well, partial perpendicular. Yes, the question was about how does partial perpendicular compare with fully perpendicular MTJs. The thing about partial perpendicular is you can use the same materials that you use in standard in-plane, and you use various capping layers and free layer engineering just to take some of the anisotropy out of the plane, but while keeping it in plane at rest. So the advantage is you can use the same materials that we know well. With perpendicular, you typically use a different material set in order to create it fully perpendicular. Although that's changing now, actually. You can use the partial perpendicular effect and take it fully out of plane. So that's another interesting area. Well, right now the in-plane is better because the switching currents and the TMRs are higher. I mean, over time we hope the perpendicular will become better. But as I showed you in one of the slides, both of the technologies have this issue where in order to get to very low write error rates, you have to drive higher currents through the device in order to achieve that. And so we have this other new structure that will cut down on that too. Great.
All right, thank you very
Thank you.
So thank you for joining the session. As you will be invited to a poster session in the lunchtime in the same building in the lobby. And the afternoon session 3 and session 2 and 3, it will start at 1:45 and in the 2 parallel session rooms. Thank you.